Thank you very much, Craig. So for the purposes of this meeting, we reanalyzed a large volume of data, and every piece of information I'll show you and every graph is fresh and new and specifically put together for today's meeting. These are the topics that we'll cover. What is the size of the normal aorta? How fast does the aneurysmal aorta grow? How does aortic size influence natural complications? What about that aortic size paradox for aortic dissection that Diana Milowitz mentioned? And moving beyond size with new dissection genes and moving beyond size by imaging wall stress. So the papers that we published over a decade and a half ago on the natural history of aortic disease were based on about 230 patients. The data that I'll show you today is based on over 10 times that, about 3,200 patients. What is the size of the normal aorta? It's not so easy to get a handle on the size of the normal aorta. There's not that much written about it. What we did was we were able to gain access to the MESA database, the multi-ethnic study of atherosclerosis. And these are thousands of normal individuals, all of whom had MRI scans. From those MRI scans, we extracted the size of the aortic root. And please note that it almost follows a bell curve, but the tail of the bell curve to the right is wider than the tail to the left, indicating that a large aorta can have many different sizes, but your aorta can only be so small and still meet the needs of your body. When one uses the logarithm of size, it becomes a bell curve, and that's called a log normal distribution by statisticians. So aortic size follows a pattern very similar to other body characteristics. But look at this, the mean aortic size in the root was 3.2. The smallest was 1.6 and the maximum was 5.0. And there are very, very few patients out here. There was no one, in almost 4,000 patients, there was no one with a 5 centimeter aorta in the normal population. This is very different than what we're used to seeing every day. I think we get a skewed view at aortic centers of the size of the aorta. It's really a pretty small organ. How fast does the aneurysmal aorta grow? Well, this is the histogram of the size distributions of the patients about whom I'm talking to you today. And we'll look at the growth in 3 categories: ascending in arch, descending, and thoracoabdominal. We found in this current review for today's purposes that the ascending aorta grows a little bit faster than our early calculations at 0.2 centimeters per year. The descending grows at 0.26, and the thoracoabdominal grows at 0.23. And the descending is statistically different. It grows a little bit faster than the other segments of the aorta. Here you see the growth rates based on size. And please note that the bigger the aorta, the faster it grows, and it's a pretty powerful relationship. That's for ascending. Similarly for descending, the bigger the aorta, the faster it grows. And similarly for the thoracoabdominal. And as you see here, the descending grows a little bit faster than the other regions of the aorta. How does aortic size influence the natural complications of aortic disease? This is the breakdown. We use different subgroups with appropriate data for various calculations that I'll show you. And this is the number of patients in the ascending and arch, descending, and thoracoabdominal aortas on which this data is based. So when I say complication in the next few slides, I mean any complication, being rupture, dissection, or death. This is the original graph that we published a decade and a half ago, and it pretty much holds true, is my message from today, on 10 or 12 times more patients analyzed. Here we can see that as the ascending aorta grows, there's a stepwise increase in the risk of these natural complications of rupture, dissection, or death. The same for the descending aorta, stepwise increase. And these are pretty big numbers, 11%, 17% for the large aneurysms, for all the complications grouped together, rupture, dissection, and death. And here for the thoracoabdominal aorta. When we put them all together in this graph, we can see that for all the locations, as the aneurysm gets bigger, the natural complications increase dramatically. And we can also see that within any single size range, the thoracoabdominal are the most powerful and most virulent players. Now, what about this size paradox to which Diana referred? I think it bears some careful examination. This is the IRAD paper to which Diana referred, and if you use a criterion of 5.5, a little bit more than half the patients presented before that proposed intervention criterion. But let's look at this with a critical eye. And please note that in this analysis, this is everybody who presented to the IRAD centers with an aortic dissection. So we know the numerator of dissection patients, but we have no idea about the denominator. So let's look at that denominator a little more closely with arithmetic analysis. By the way, we noticed the same thing. You can see here that we also had some type A dissections in the small size range. We noticed this a good number of years ago. Type B dissections as well in the small size ranges. And when you put them together, a fair number of dissections in these small size ranges. But here, let's look at this bell curve, and let's focus on the tail of the bell curve. And please note that as we move from the really large sizes towards the minor enlargements, the number of patients increases dramatically. The tail of the curve gets much, much fatter as we come in from these very large sizes, which we know are distinctly uncommon from the MESA data. So here's the arithmetic. These are the different size ranges. These are the proportions of dissections in the IRAD study. You can see that the majority of them were in pretty large aortas, but a minority of them occurred in small aortas. But again, we did not know the denominator. Now, from that MESA study, we know that there are very few aortas in these large sizes and an awful lot of aortas in these small size ranges. So that means there's a lot more potentially susceptible patients. And when we make the ratio of numerator over denominator, that is the observed dissections over the segment of the population in those small size ranges, these are the numbers that we get for relative risk. And when we correct this using 3.4 as the reference range, if you have a 4.5 centimeter aorta, you're 1.5 million times more likely to suffer a dissection than if you have one of these small aortas. So with this interpretation, using both the numerator and denominator, we find, yes, these dissections do occur in small aortas, but they're extremely infrequent. And just as the IRAD investigators did, they recommended no change based on this data in the intervention criteria. So the bottom line is, yes, you get some dissections, but proportionate to the huge number of patients with those smaller aortas, it's a very, very, very uncommon phenomenon. Now, Diana beautifully talked about these syndromes, the Loeys-Dietz and the ACTA2 and the MYLK that predispose to dissection at small sizes. And it's time to incorporate this in our decision-making algorithm. We do sequence everybody. If we see these mutations, we're likely to operate earlier than we would otherwise. But I'd like to focus for the next minute on two single base pair changes that are also relevant to surgical decision-making. Diana and Scott Lemaire and her colleagues identified this RS181 mutation in the fibrillin-1 gene and found that it correlated with aortic dissection. Just 3 days ago, we published a paper that confirms that, and you see that that single mutation, that single base pair change, doubles the odds ratio of aortic dissection. Our paper was able to show additionally that this is a powerful enough phenomenon that it overwhelms size. It's still significant if you take size out of the equation. This one is not yet available for clinical testing. But we also have this other single mutation that we recently identified on the KIF6 gene. Now, this gene is already available for clinical testing because it was involved in the genesis of arteriosclerosis. You can order it from Quest. It doubles your patient's odds of having an aortic dissection, and we've just started using this actively within the last year. So you can order the KIF16 gene as part of a cholesterol profile, and if you see that it's positive, you know that that patient has a double likelihood of dissecting. I think we're at the point now where we have to start including this genetic information, molecular genetic information, in our decision-making strategy. And finally, in terms of wall stress, as you know, like we're doing here in one of our engineering laboratories, we can measure the mechanical properties of the aorta very well in vitro, the excised human aorta, and we generate these beautiful curves. But of course, we'd like to be able to measure those mechanical properties in vivo in a living human being. And as we see in this beautiful MRI from Northwestern University, the imaging is just reaching extraordinary levels of complexity and accuracy. And these advanced 4D MRI images purport to calculate wall stress. And they're able to do that. And I think soon we'll be able to incorporate this information in our decision making. But I want to mention two caveats. You all remember from your college physics that to calculate stress, you have to have some measure of force. You can't calculate stress just from three-dimensional anatomy. You have to have some measure of the power of the force on the cylinder. And please be aware that these algorithms for these beautiful imaging techniques often make assumptions that are not completely valid. They may assume an elastic modulus in order to be able to calculate force, and they may not measure blood pressure at all. You have to either know the elastic modulus or you have to know the blood pressure very accurately at the time of the exam. So to summarize, the normal aorta is small, mean of 3.2 in the ascending aorta. It's a lot smaller than I thought it was, and we get a skewed view at aortic centers. The aneurysmal aorta grows a bit faster than we appreciated a decade and a half ago, about 0.2 centimeters per year. Very powerful relationship. The larger the aneurysm, the faster it grows. This data shows that size continues to be a strong predictor of natural complications and a suitable criterion for intervention. The dissection paradox, I think, is largely explained by the huge number of patients with small aortas who have a real but very, very unlikely possibility of aortic dissection. The KIF6 and RS181 are promising new, you can use the word maybe dissection genes, and the KIF6 is currently clinically available for your use. And these new diagnostic imaging techniques will, I hope, add valuable engineering data to our decision-making strategies, but please keep in mind the inherent assumptions that make those data not quite as accurate as the pretty pictures that we see. Thank you for your attention.